Assalamu alaikum. Hello, everyone, in another session in MLScale. Thank you, everyone. Thank you, Devmena, for having me, and thank you, Dana, for facilitating this session. And I hope you will learn something new and you will enjoy the session. Before we start, I'll just kind of do a quick reminder of what we've seen previously in this series. So, in the previous series, if you check kind of the YouTube channel from Mena, you will find that we kind of went through different topics, especially kind of regarding contrastive learning, and you will see also the current session is right now. But you will see different, you will see different sessions that are kind of on how to train your clip model and how to do a lot of actually cool stuff that we've seen that is still relevant in kind of in today's session. And the one that I'm interested, or the thing that we are really interested in today is two things. First thing is this one, which is the masked modeling. And then there is also, I'll say, there was one for contrastive learning. Yeah, this one, the picture perfect phrases. There is this one too. So these two actually are the main kind of topic that we will use this time, but it's not. We are not only talking about it in I'd say in a theoretical or a theoretical talk, but it's more like a practical deployment that is seen in the industry right now. So when you are trying to build your rack system and you are trying to create a kind of use any vector database, you will see that you are trying to use something like an embedded model that is used to generate vectors from your input, or use embeddings, generate embeddings from your input. So, for example, you might be interested in using embedding GenMap, which is a model that is coming from Google to actually do this task specifically. Or you might be interested in using any other models that are available out there, or you are interested in using the grade, the industry grade models similar to the models that are blocked behind paywall, similar to GPT, GPT-2, and also GPT embeddings, and also any of the embedded models from Google or anything like that. And all of them were actually trained using similar recipe, which is the first part that we've seen previously, which is kind of using masked modeling to actually do just help the model learn the representation, the general representation from a massive data set without using any labels or anything, which really kind of lower the cost for you to go and collect high quality data. And it allows the model to just learn from unlabeled data that is available in abundance in the internet. Or you can actually just find a data set similar to FineWeb, where you can actually train a model using that. And then you can do the fine tuning on a smaller data set. And during that fine tuning, what you are trying to aim for is not the model learning representation, but it's more alignment of the model. And what I mean by alignment is just the model will need to produce a high quality evidence for the same knowledge. So if you pass it two phrases that have different, I'll say, ways to express a knowledge, it needs to provide you with the same vector, with the same actually, or two vectors that are close in space instead of just two vectors that are far away in space and scattered in space. So when you are doing only the masked modeling, you will learn representation, but that representation will not be, I'd say, of high quality. So what you need to do after finishing the pre-training phase, you will go and do the post-training, which is, or the post fine-tuning, which is just doing alignments and helping the model to learn better representations. And then later on, you can actually deploy this model and put it in Pinecone and just use it with Pinecone, use it with Webgate, use it with any rack system or any vector database that you have to build any rack system. So today we will go through the phases of kind of briefly, and then we will see just a way that you can actually evaluate these two models, or this model on a data set or on an evaluation data set or an evaluation benchmark is called MTEB that is available from the Hugging Face team. And then it will allow this, like MTEB will kind of allow you to rank or just like see how good is your model compared to the rest of the models. So if you went to MTEB in Hugging Face, you will find there is a list of models with ranking, and then there is, I'd say, the zero shot accuracy of each model. So now the best model that is available right now is like the Embedding Gemma. Like it's a fine-tuned version of the Embedding geometry, or they just like extracted geometry this company here, and they built like a kind an embedded model using it, and now it's telling you that it's achieving like a 73% zero shot, but at the same time it has better, I'd say, like other metrics, and you just like make it smaller so you can actually you can have a better understanding. So the mean task, like for each task, it has 72% accuracy. And then there is like, I'd say, each task specifically, how it performed there. Sometimes it fails, sometimes it performs better. But the main goal is to actually have a good enough like results so you can actually say that your model is can actually be used for production. For the zero shot, it's a bit like tricky since you will give it a bit of context to do this. But for these tasks, you don't know what's happening, so you will just like do the embedding generation, and then you will provide that embedding to the model so you can actually have like a representation and then you evaluate them. The thing that is actually a bit more interesting is this one, which is like how does these models, like how big are they, and how good is like like their performances. So like if you see here that this is the x-axis is like the number of parameters a model have, you can see that it's up to 100 billion, like to 100 billion parameter, and then there is models that are kind of just 10 millions, and then they still perform good enough for this task. And then, for example, the difference between this one, the bilingual embedding small, and this one is just like kind of 10% ish or something like that. So you can see that like even 100 million parameter model still performs as good as like the 100 billion parameter models. So this task is a bit tricky. So it's not about like how big is the model, but it's about how good your like model learned, or like how good is your model when it was learning. And this is like I would say the one of the most interesting tasks right now, especially since like you cannot just defeat it with bigger models. So you need to craft a really good recipe for training where you can actually like I would say have good representation. And one of the tricks they used even in like the embedding Gemma. So if you went to the embedding Gemma technical report, you will find that they use also the same approach. So they took like the pre-trained Gemma that is pre-trained on large amount of data using MLM, and then they actually fine-tune it. Wait, like let me check. Where is it? Where is it? Where's the faces? Yeah, this is the recipe. So they have like the training, the encoder decoder training, and then they do the pre-fine tuning, which is they take the initial like the model that they trained using MLM using kind of the T5 Java, and then they did like I would say pre-training on like kind of um, just to improve the generalization of the model. Here they just like still use the like unsupervised data to actually do that, and but then there is like one actually of the phases where they did like this one to find the post fine tuning or the fine tuning after finishing the model, where they will train it on like really small amounts of data that is really task specific, and they actually try to make it really good for specific, let's say, topics, and then you can actually use that like base model to actually create as many models on those subtopics that you are interested in. And for the initialization, not evaluation, there was like actually a good here um, in this one here specifically. So there's like too many objectives. It's like if you read through this like kind of training recipe itself, you'll find that they have like kind of a specific I'd say like just kind of prompts that they use to actually train the model. And then for the first phase, which is just like kind of having, let's say, like just doing the MLM. And then for the second phase, which is they use the noise contrastive estimation, which is like something like SEM-CLR use for their own image, like contrastive learning that we talked about before. And then there is like the post actually, like the post fine tuning, or the fine tuning where they need to do, I'd say, just kind of like alignment problem, which is they use this loss that use like the square of the dot product to make embeddings actually orthogonal with each other, and then they just like combined all these losses in the pre-training in the fine tuning part. So in our case, we will go through something that is similar. I just like try to get a TPU spot on Kaggle so that you are 29. Earlier it was like 40 on the queue, but now it's 29. So we will come back to the scripts, but first let's actually go through just like kind of the normal way you actually pre-train an MLM on a fine web. I think we used this data set before, if you remember it. It's one of the actually foundational data sets right now in text. It's around like 100 terabytes of data, but you don't need to like load the whole data sets at all. You just need to stream it directly from Hugging Face. And like by streaming, I mean like just like kind of downloading only like kind of batches of the data as you need it on your own for your own actual iteration. So it does not require you to download anything and save it on your own drive. So you just like get it from the internet, keep it in the memory, and then use it for the prediction. And after the prediction, you discard it and get the new batch from the like again from Hugging Face. And this way you don't need 100 terabytes of data just to kind of save it like a laptop or anything like that, which kind of makes training really like cheap. And you can actually even do it on let's do ImageNet. Yeah, you can actually even do it. What is it? You can do it even on ImageNet. So you can actually even do it on ImageNet. You just need to have like a shuffled data set, which is like here. You can actually find it here. So you just need to have a shuffled data set, and then you can actually just like stream images directly from Face to your laptop without needing to download all this 100 gigabytes. Right? And the beauty of it, like for example, when you are using like, let's say Colab, or you are using Kaggle to do like just like your training to test like your hypothesis and everything, it does not require you to download these data set to the drive of Kaggle. You can actually just you can just like stream it. And this is actually the only difference between streaming and not streaming is just this. Let me actually show you. So here, when you are trying to load the data set, this is like Hugging Face. Actually, it's like version this. So when you are trying to do load data sets from Hugging Face, you'll give it the ID or the name of that data set, which split you are interested in, and then you will just like say streaming equal to true, and this will automatically just like I'd say just load as much like batches as you want from the data set, and without actually saving it on the device. So you will save space and also compute not compute, but you will save mostly space on your drive. Your like your notebook and your server, your computer server will not crash because like there is not enough space in it. So let's go through the scripts like one bit at a time. Let's check first if we got no, we did not get it. We're still 29, which is fine. Luckily, I run this 3 months ago, since this talk was supposed to happen 3 months ago, but I miss some sessions. So there is like first, like you will install tick token datasets and weights and biases, and also MTEB, which is the dataset that we just talked about in the leaderboard. And then you will use like Kaggle secrets to actually load all the secrets like the HF token and the weights and biases API key. You can get the HF token from here. You can actually go to Hugging Face and then go to this to your icon here, and then go to access tokens. Then it will require you to do like your password, and then just like you can ask it. You can actually just like ask it, find create a new token, and just create a token like that is for reading. You don't want to write right now, so you want to read. But if you are trying planning, for example, to upload your data sets to Hugging Face after you finish, if you did any post, like any pre-train, any like kind of editing or anything to the data set, and then you want to actually put it on the drive, you need to do writes for the data set, or you can just like do a fine-grained one, and then you can actually define, I want to read, and then I want also like kind of writes and in the data set too. Which is also good. Give it a name and then take that token, and you can add it directly from here. You can just like give it a name and then put it here. And then when you want to use it, you need to set these things in the OS I'll say on your machine. You need to actually define these things. So you need to get them from Kaggle secrets and then put them in the machine using these, like it's just like environment variables using this kind of syntax. We need first the HF token, the weights and biases API key, and also the weights and biases entity key that you can get from weights and biases. It's like when you are trying to run the notebook, they will give you a link. You click that link, and then you can actually get that token, and you can put it here in this place here. And then for the weights and biases entity, just like your username, where you want to actually upload those datasets. I've did some cleaning here, just like to kind of remove any checkpoints if you have any checkpoints, and then you move to kind of the script itself. We will be using Jax and Flax and also Optax for this, and tick token for the let's say the encoding, since it's faster than the one from transformers, like the auto transformers. This is actually faster, so I really prefer this one. And then we import MTEB, which is the one that we use for the evaluation. We will create a mesh for like kind of training our model. So we will create a mesh of 4-2, which means like we are splitting the batches over 4, and the model, each CPU will have each two TPUs will collaborate on the one model, and then each fourth, like kind of, since we have 8 CPUs, we will split them like kind of by 2, 2, 2. So we will have 4 like available TPUs. So we will split the batches, the data over 4. So this is like kind of SMPD, or like something similar to SMPD, but like not for like it's not on a single device, but it's for a multiple device. You can actually get more information on this here on some docs that I just created. They will be sharing later on in the future. But let me actually share it with you, so you can actually share it. You can actually get more information about it from here. You can actually go to scale, and you will see like all the like strategies that you can actually do if you want to train like kind of multiple them. Like this is what we are trying to do, like kind of this TP. But there's different strategies that you can actually try based on the available amount of compute that you have. We will have a tokenizer, like we will define the tokenizer. We're using GPT-2 tokenizer. I know it's not good documented, but for now, we will just keep using it for just like this experiment. And then we will define a transformer block, which is kind of typical transformer block. The only difference is that now, if we have a mesh, if we have like a GPU of 8, we need to make sure that the kernel is actually split across this axis that we defined here, like the model axis. So we will need to know that each kernel or each weight matrix or each weight vector is split across these two devices. And then we will have the second linear things, the second linear that will use this kernel init that we defined here to actually init the model itself. And then the same thing here, the kernel init. And then we will be using just like Jalo linear, Jalo second, which is something similar to what we did previously. The other thing that we will have is other positional embedding. People moved away from this positional embedding to rotary embedding. But for now, this is like an experiment. This is a kind of small notebook to actually just show you like how you can train a typical bird. And then a mini bird that will kind of combine these like two blocks, which is the transformer block and the transition token position embedding, to create a model for us. And then we have an output layer that is as big as the vocab size. So for each word you have like in the vocab size, like in GPT-2, it's about 50,000. So the output layer here is like 50,000 kind of neuron for each neuron will be responsible for let's say a word. And same other thing, we will use like NX with partition in, and then we will like name shard in, which will kind of shard this kernel by the model itself, and then we will have a bias in it with the same shard in. Even though we don't need bias for this data, since we turn it to false, yes, we'll turn it to false, but just like kind of setting it to just make sure that we in the future. And then there is like the call, which is when you call a model with inputs, you will pass it through all the layers, and then we'll give up like the output of the model. And then this is when you want to call this model after you train it and after everything else. So you want to still like pass it through all the layers, but the only difference is that you will not pass it through the output layer, since we don't want to transform these like embeddings that we have here to like kind of tokens, or like to like kind of, we don't want to predict the next word. We just want to predict all the vectors that are available with the knowledge that we have, and then we use that knowledge to actually condense it in a simple place that we can actually, or a simple vector that we can actually use for our vector database. And then you create a model using how much, like what is the maximum length of your model, what is the vocabulary size, like for us, like in for GPT-2 tokenizer, it needs to be 50K, 50,000. And then the embedding dimension, this is like kind of just like what is the dimension of each neuron in our model. A number of heads, usually 12 for typical transformer, and then feed forward is like usually 4 times the embedding dimension. So if you put here 768, you will find there's 3,000 or something like that. And then the number of transformer blocks, typically for us, a base transformer, you will get like 12 layers here. And then just like the RG, and then this is where it gets 100%. So here, we will use something that is different than GPT, than actually this is the original actually masked like language model, which is like each word will have the ability to access any word in the whole sequence, and you create a matrix like it's like kind of just it's a full matrix where you can actually create a mask swap. So you don't define like a kind of matrix of attention here, since everyone is able to access everything. What you try to do is like kind of pick words from the from like the input vector that you have, from the tokens that you have, and then you will mask them based on that to create tokens, and then you create labels, which is like the next, what is the what are the words that you actually retracted from what are the words that you mask you are trying to predict. And then we will create like a kind of processor for the dataset where we will take each like kind of phrase in fine web since like it's not labels, and then we will try to create like our own say our own phrase. This is like on the go. So we'll create our own phrase, and then we will put like just like inputs and also labels. And if you are familiar with GPT-2, you will also add attention mask. But for us, like since we only are interested in this, and we use the mask actually to do like a kind of like, replace the text with just like, replace a word with the token mask itself, that it turns to be like a bit different. For the loss function here, for the first one, which is like just the MLR, you when you pass the model the input, you will generate like all the logics, and then you will try to predict only the missing words, which is the labels. So you will your logics like you remove like I'd say you will remove the words that you don't want by kind of getting rid of the mask, just like kind of which parts of the mask you have. Like if it's kind of masked, then you will skip it. If it's not, then you will keep it, and then you will try to calculate the value of the loss on that mask, and then you will divide it by the number of masks, and like creates for you a mean ish for that. And then you will use it in your training step to do that, just like kind of just an X value grade with the function, the loss function, and then you will pass it and you will use this graph like kind of the graphs that you calculated to update the model itself. Then you will return the model for the next iteration. Similar thing for the evaluation. And this is the way like after you train the model and you define everything. Um, you will have the ability to actually just like take the weights that you trained and put them into this kind of container that is like compatible with MTEB, which basically just like calculate the mean pooling. You need to have this function. You need to have this function in your own content, in your own like wrapper, so you can actually just like put it inside the MTEB like dataset, MTEB library, and then you can actually do just like the evals automatically without writing a lot of scripts later on. This is just like the script to call the data set, just like a script to call like the training and everything. I just like define the data set loaded from using streaming. And then you will split it like there's a training data set when you will actually take only like just take you skip the validation sets, and then there is like the validation set where you will take only the first amounts of like the validation set itself, and then you will create two iterators out of it, and you need to drop the last batch or else like um, you will destroy, or you will try to you will not destroy, but you will create noise for the layer normalizations and also for the batch normalization if you have any of these layers, like since they rely on the batch of say statistics to actually update their weights. So if you don't drop this batch, sometimes like there will be a batch with only just like 8 examples, but your usual batch is like 32 batch, for example, 128 batch, but sometimes like the last iteration, you will only find 8 elements, which kind of like it does not let you optimize well. And then we will have like 4 iterations. We will just like kind of try to get the next batch. And then if there is like any problem, like stop iteration raised or anything like that, we will just like stop iterating. And then if there's like we will define the sharding for the itself, and then put like the devices like the data sets, we will try to shard them using this sharding here, and we will try to split the data itself into kind of different devices, so we can actually prepare for actually this distributed parallel training that we talked about. And then yeah, and then you would call the training step, which is typically just like the training, calling the model itself. Then you will log the loss here, and so on, just like physical validation, which is similar. And then if the model is good, you will do the checkpoint. And I think this is most of it. But the most important thing is like evals, like if you want to evaluate on the MTEB, which is the one that is a bit interesting, which is exactly this function here. So when you want to evaluate, you need to load the model. When you load the model, you need to load it with all the batch stats, all the like stats, all the optimizer stats and everything. And then you will take only the model weights that you are interested in. So first you will create a model just like from the config file that you have, which is just like kind of you pass it here, which is like it needs to be the same config file as the model that you used previously. Once you initialize that model and then you split it, you will try to load, I would say, a checkpoint that you saved previously, and then use that checkpoint to actually update the resolved model with the parameters that you got from the saved model during the pre-training. And then you will define with that model, with the restored model, you will define with a mini BERT for MTEB, and then you will give it the same tokenizer and the same max time that you define. And then you will decide, like, start like just like hand selection from the list of like data sets or the list of problems. If you go back to MTEB, you can actually perform a task. You will find that you will create it there. So there is like many tasks that you can actually like you can actually evaluate your model on. So you will just like pick what are the tasks that you are interested in, and then you will just like create a list of like a list of like tasks, just like the task names, and then you will use the MTEB library that you I'd say you actually imported at the beginning in the imports, and you will give it, you will tell it, okay, these are the tasks I'm interested in. Can you please like kind of give me the code only to run these tasks? So you will pass it the tasks, it will define the evaluation, and then you will take that evaluation object, and then you will run it on the MTEB model that you defined using the wrapper that you have, and you will ask it to like put all the evaluations in this folder here that you can actually get a JSON object that has all the details that you need for how good was your model. And then you will ask it, okay, can you do this for the evaluation splits? And that's it. Like just you can print it after everything. You can either print it or you can actually just log it to weights and biases. I like to log it to weights and biases so I have everything in like just like one single place. And then there's just like us trying to run like just like all the scripts that we talked about. There is the main pre-train, and then there is the main eval, which is like calling these two functions that we defined for pre-training and evaluation. If we are able, if we're lucky to actually get a spot in the TPU, we might run it like fast on the CPU and see if we can actually get some quick results. But there is already results here from the previous one. So we can go to this link here and I can actually show you how good it was ish. Again, this is just like a small model. So if we're able to get 30%, that will be good enough. Yes. So these are the three data sets that we selected. There is like STS benchmark. So we got a score of 38% with this, our own kind of model. And then there is this data set, the FIQA. We got like a score of 0.007. And then there is the banking classification where we got like 39%. So if we went to the SES and let's go to the SES MTEB, you can find the SES. Let's do this. So SES benchmark. We need to filter it. Filter. So this is it. So most of these models get around, let's remove this one. You can actually, we can click our own results. So most of these models get 98%, 90%. So our model itself is still a bit like kind of not that not that performance to actually compete with these big models, which means we need to train it more and we need to make, yeah, but there is like still models that have something similar to us, which is like, for example, the Delta. It has like 41%. It's like we're not the only ones that suffer here. So there's like there's other models that are on the benchmark that are still kind of giving results that's closer to us. And then there is like, which means like, okay, we have a good model like to actually put it in the data set, just like from one, we have a model that we can actually upload to the benchmark, and then one that we did like for 7 hours on a V3 TPU and like kind of like a TPU V3, which is like kind of the old TPU that is no longer available for reward. Now everything is moved to V5, and you can get it for free, just like from which is really cool. And this is the loss function. It's like kind of you can see that the model is learning here, but everything here is just like kind of doing the pre-training. For the script that is available here, I'll share it with you too, but I'm not sure if I will try to run it after this one. We will just go to we would go to the scripts of like how it's kind of working, and we can actually see just like the reverse. So everything is almost the same. The only difference is that we added this one, the train step contrastive, which is the one that uses contrastive learning to actually train on a different data set, which is called SLI. And then we use that data sets. If I can actually, this is the main contrastive tuning, which is just like we will use the same thing. We will use the checkpoint that we saved from pre-training, and we will use like the contrastive prospect, which is CMCSE, which is like kind of interesting loss that is similar to CMCR itself. And we will be using on this data set, which is SNLP. So it's almost the same actually batching, the same name sharding and everything. The only difference is the loss itself and the way we load the data, which is just like kind of there is one new axis here. So there is like a kind of, since we are doing pairs, there is like an axis here, a new one that is 2, which means that there will be, I'd say, each batch has 2 elements, or each, like not each batch, each item from the batch will have 2. So you can actually use this to actually like pass a pair of data, which is you will give it 2 phrases that will contain the same information, and you will be able to calculate this loss here. We will be able to do the parallel the parallel training using just like the same, I would say, almost the same axis that we used before, which is the batch. So you don't need to redefine the shard, and you don't need to define the mesh again. Like, you can actually keep using the same thing. Guys, already fit your own model. And then the only other difference is nothing actually. It's like you will use the same thing. Like you will do the main pre-training, you will follow it with the main classic learning, and then you will do the evaluation. So the only thing that changes this one. And in this one, we are only doing simple stuff, guys. I just like to help the model align there. And this is the similar strategy that is mostly used in the industry right now to actually align these models with their own, let's say, data and with the right focus on knowledge itself, not on anything else. We'll check if you have any questions. Let me share with you the second notebook and then the first notebook. And if you have any questions, feel free to ask since we reached the end and we did not get that much to get it together, which is fine. This is fine. Yes, you are live. I will try to save like an example. I will try to save like the same thing. I will try to save the notebook, and then you can actually access it. But you can actually access it now with the results. white will be just like empty. I'm not sure if I can make this public. Let me see. I don't think we can make it. Copy to workspace. One more of, yeah. Well, we try to make a report out of this. You have any questions? Feel free to ask. If you don't have any questions, then we almost reached the end of my battery for the laptop. 20%. All right, no question. If there is no question, thank you very much for attending this, for watching this later on. Hope you actually learned something new. And until the next one, we'll see you later. Assalamu alaikum. Assalamu alaikum.